Yeah? Okay. So welcome to this talk. Thank you for coming. My name is Suneet Rikhi. I'm a visiting professor of practice in IIT Bombay, specifically associated with SemiX, which is the Center of Semiconductor Technologies at IIT Bombay. The professor in charge is Udyan over there, and I was the first professor of practice who joined about a year ago. This is my third visit to IIT, and the it'll be my attempt to demystify what a fab is, or at least to provide some framework within which you can go dive deeper if you have to, or would like to. Um, it's in terms of detailed accuracy versus simplification, I have gone on the side of simplification. So none of what I have to say should be taken as a blueprint to build a fab, for example, but it should be taken as a framework within which you can increase your understanding in the area you have chosen to seek to understand. So the basis of this talk is that nations around the world are racing to secure strategic positions in a growing and critical semiconductor industry. And India is no exception. And a couple of announcements have been made. And it looks like we are headed towards fabs in operation in India. And so it is very timely that we talk about what these are and what we, as a part of the semiconductor ecosystem in India, and specifically education and research, and I'm talking from the point of view of IIT Bombay SemiX, what we must do in response to this wave of semiconductor manufacturing that is headed our way. So that's the basis and the overall view of why we decided to give this talk, and hopefully you will find something of value to deserve the time you're spending with us. So before I begin, I want to make sure where the talk will focus. There is this process of design of the integrated circuit, which leads to a tape out, and it goes into a wafer fabrication, which we call fab. And then after that is done, assembling individual chips and testing them at a unit level are all done by the purple box called assembly and test. And I would just want to, before I begin, I want to say that my focus will be in the wafer fabrication. That is the focus. Although in Q&A, we can talk about anything left or right of the center box. So to start with, here come the semiconductor fabs. Who are these? So one of them, which you all must have heard about, is Tata. And Tata has decided to have a fabrication facility, wafer fabrication facility in Dholera in Gujarat. It's going to start construction this year, and based on my experience, it'll be impressive if they start processing material within 2026. I wouldn't be disappointed if it slips into 2027, but that's the estimate. Meanwhile, Tower Semiconductor, which is an Israel-based company, not unknown to India because of their presence in various forms and their previous proposals, has a proposal on the table for their fab in India. But that fab has not been announced because that is under review by the government. And hopefully there will be more coming our way, and India will become what it seeks to be, which is a semiconductor manufacturing hub. So those are the fabs that are coming, the first fabs. And now I want to say Let's start with that red big box called fabrication, wafer fabrication, and just look at what its inputs are and what its output is. So the inputs are blank silicon wafers that are sliced out of ingots, silicon ingots, highly purified silicon, and they go into the fab as blank wafers, and they come out with a lot of chips, which are called die. And after the fab is done and the output wafer goes into assembly and test, then it's sliced and diced, and the chips are assembled and tested. So Tata has announced that the fab will be 50,000 wafers per month. And again, based on my understanding and experience, 50,000 wafer starts or wafers per month capacity is in the nominal range of a fab. So now let's go to what are semiconductor fabs. So I'll start with a tour. So you'll go on a tour with me to the fab. We will experience what's happening outside, inside, construction, all that stuff. And then we will go into how does it operate and on and on. So we start with a tour. So let's start with this photo. This photo is from the Intel Museum in Santa Clara, California, and it's just tries to show what a fab clean room looks like. And if you notice, it's kind of yellow, and the yellow is because yellow light is friendly to one of the most important steps, which is lithography, to make sure that using normal light, you don't inadvertently mess around with the resist that captures the image. But more on that operation of what the fab does later. But this clean room is 10,000 times cleaner than a hospital operating room. And so it has to be respected. A lot of discipline, a lot of protocol, a lot of infrastructure goes into ensuring that that room is that clean and stays clean. This quote is from an organization called vSemi, or sorry, not vSemi, Semi, and I just took it on faith that they know what they're talking about when they say that the fab clean room is 10,000 times better, cleaner than a hospital room. But that room, that clean room, is just a part of a tower, a structure, and you can see that room is now shown in that whole tower. It has 4 major levels. One is called, the top one is called interstitial level, or commonly known as fan deck, because all it has is fans and filters. And based on that, its job is to keep the air clean. It takes circulating air coming up from lower floors, and it sends air down, clean air down, and that's how the whole thing works. So it takes a large amount of room to do just that small job of keeping the fab clean. Then, of course, the clean room level, and that's where, if you think about that, that's where the equipment is, that's where the wafer processing is, that's where action is. But below the clean room is a sub-fab level. And sub-fab level has transformers, power lines, cables, pipes that deliver chemicals and gases and all that stuff. And in fact, some of the tools that you see above in the clean room, they are like icebergs. They have their bottoms down there in the sub-fab, depending on what the tool is. So the sub-fab supports the fab above in supplying chemicals, materials, and electricity and all that stuff. And then below that level is another one, which is called utility level. This is where giant chillers, and when I say giant, they are giants. The chillers, main power large ducts, big ducts, whether they are exhaust and waste or supplying the sub-fab with distributing of the chemicals and gases. So the utility level is the larger part of the sub-fab, if you can call it that. So that's the fab. That is what a fab is. Now, let me talk about what it takes to build it. This is Intel's Ireland fab. I don't know whether it's still under construction or recently completed, but it has some data that's interesting. The earth that is moved to get this fab constructed is more than 1 million cubic meters of soil. The cables that are laid out in the fab go 9 million meters. And, at any given time during construction, there are 5,000 trade labor. In spite of all the automation that is involved in constructing such giants, 5,000 people are working at one time. And finally, the cement and the iron reinforcement, the amount of cement and the reinforcement that is used is 2 times that which was used in the Burj Khalifa in Dubai. So the scale is just tremendous. So that's why I call this an engineering marvel. Now, this is from TSMC 2023 July update. I chose this TSMC image to just give an example of what a fab does. A fab actually spawns a city around it. Beyond this itself, there will be buildings from suppliers of tools and equipment for maintenance, so that they are right close to the fab when they're needed. So this is the scale at which a fab is built, is being built. This is the Arizona one from TSMC. Now let's go from the outside to the inside. So we're going into the clean room. So in the clean room, you will see this row of equipment that is really boring looking. They are like refrigerators that you can't even open to see what's inside. They're just big blocks of metal, rectangular in shape, some wider than others, but they line up. And there's one thing in common with all of them, and that is wafer ports. So it's like going to your fridge and trying to open it, and you can't open it, but you can ask for milk, and the milk comes up. So that's the only way to interface what needs to be processed or what has been processed. So those are called wafer ports. And then above, you will see in the ceiling, there is these wafer transport robots that are coming in. They stand on top of the load port or wafer port, and then they lower the material into it, and the tool takes it. And I'll talk about that in a second. So before I move on though, this is called the bay of a fab. A bay is, as opposed to something else I'll come back to, the bay is where the tools are facing. You can walk down the aisle and you can interface with the tools if you're a human, but why would you? Because of so much automation. In fact, since I started, I didn't introduce myself fully. I spent 31 years in Intel, and I was in their technology and manufacturing group doing various roles, senior management roles, including at the end last 8 years, I built up the Intel Custom Foundry, which is a precursor to the Intel Foundry services. But when I used to go in the 1980s or 1990s also into these bays, the bays were wider. You could have 4 people go back and forth because there's that much activity going on. Over time, in the newer fabs, the bays have become smaller, thinner. And that's because you don't need people to have those lanes. So this is one example where, the highways inside the fab could reduce their lanes as opposed to increasing all the time in a place like Mumbai. So that's the bay. Now remember the load ports. So load ports take wafer carriers and in and out. And this wafer carrier was, the industry went around and it defined for itself a standard way in which to store, carry, and interface with tools. And they defined this front opening universal pod, and we call them FOUPs. Each FOUP has 25 wafers. We chose 25 because intelligent people ran lots of software to optimize at one time how much should you process by a tool. If it's less, it's not optimized. If it's more, it's not optimized. So 25 was selected. And so each tool, each fab equipment processes one lot at a time. Now, sometimes you have, for an experimental purposes and all, you can have a lot that is not 25. Lots of slots are empty, and you just use 3 or 4 of them just to run quickly for the experiment. But we are talking about high volume manufacturing production. When the production happens, there's no question about it. It's 25 wafers per processing of the tool. And when it's done, it brings it out, and a robot is there to feed him another lot, and so goes life. And the top of the FOUP, if you notice, is like a black structure which is clutched by the wafer transport tool to take it up or bring it down and release the clutch. This is a lonely bay, a modern lonely bay, and this one is selected from TSMC's, one of the newer fabs of TSMC. One thing you should note is the raised floor. So there is a raised floor, and in between in that floor and where people walk is the place where air gets sucked in and sucked out, and that's it's perforated for that purpose. And so one of the things you have to get used to when you're walking in the clean room is that kind of a floor. It feels funny in the beginning, but that's what you have. Now, also from TSMC, I borrowed this picture because this says, I was looking for this kind of a picture because when you look up, what do you see? You see a railway network, all these monorails that the wafer transport robots are traveling, and they go bay to bay, they go within bay, and cover the entire factory or fab. Now, there is a place where humans do work, and that's behind the tool. And that area is referred to as the chase. So a fab is built out of bay and chase. Bays we talked about. This is a chase. What you're looking at, this is an Intel photo of 2 equipment maintenance technicians working on the equipment from the backside of the tool. This tool is down right now for maintenance. Here's an interesting thing. This is in Intel, it's called the 8:20 morning huddle. You have to show up here at 8:20 and then talk about equipment status, parts inventory, operating forecasts for the day, expertise needed for the day, depending on what is going wrong or what might go wrong that day, and no coffee and no cream rolls. That is sad, but it is true. Now, this is my never say never moment. I cannot believe that before 2011, I would have said that one day will come when we will be compelled to allow somebody to walk into the clean room without a gown without that protocol of clean. And sure enough, Obama came to visit our fab, and we all sat there completely in disbelief while him, his security detail and the videographers and all that stuff, they came in so that he could give a speech from the clean room of the world's most advanced fab called D1 in Hillsboro, Oregon, where I used to work. If you're interested in what he said, it's available on the White House. In fact, I took a screen grab here from that video, and he made some statements about how he knows semiconductors. So now, that was the fab. We talked about the outside, we talked about inside, the environment inside, what people do inside. Now we want to go into how the fab processes wafers. So for that, let's start by saying that it's actually very simple. You construct transistors, these three terminal devices. Sometimes some people will say, don't say three, it's four, but three or four terminal devices that once you construct them, then you just connect them to each other and supply them with power through other connections. That's it. It's simple. That's what the fab does. Now, it's like constructing a high-rise building. So one of the things is that transistors don't like to be on any other floor but the ground floor. So they all have to be on the ground floor. And so every other floor above is used for metal interconnects, the connections between transistors and to power. And so between floors, you have these posts, and those posts are called vias. So via, for example, say metal 1 to metal 2 via. What does that mean? Metal 1, first floor, metal 2, second floor, metal 1 to metal 2 post or connection is a via. But then there is a special name used for metal 1 to transistor connection. It's the same thing, but it's called contact. So you've got transistors, you've got layers of metal in different floors, and interflow connections are all supported by posts that are either called vias most of the time, but for the transistor connects, it's called contacts. So that is the simple way of looking at how a wafer is processed. And if you want to get a little more visualization, our friends at Applied Material have shared this photo, which has a much better view in my mind about how this thing is like a building, with different floors and those posts. All of that stuff is depicted by a photo I borrowed from Applied Material. Now the question is, how does a fab know how many transistors should be placed and where, and which transistors need to be connected to which others? So that, because the fab can't know that. So who knows? The chip design guy knows that. The chip design people know how the transistors are laid out and what they should be connected to. So in order for the fab to know that, we have to actually make this picture a little bit more complicated and say, for this, the fab needs an additional input. And that additional input is what we call a mask set. Or to be accurate, it's called a photomask set. And a photomask set is a set of about 50 glass plates. Now I chose 50 because it's kind of similar to what Tata Fab will face. But the much more advanced fabs of today, say 3 nanometer and all, it could be Not quite double, but close to double of these. So you got these photomasks. Each layer contains some information that then can be used to start the process of wafer processing. So in other words, you can look at it as design patterns expressed in terms of a mask for exposure of light that represents the design of the transistors and the connections. So then, this is a simple Wikipedia depiction of what's happening. You take the first photo mask, you insert that into a tool which exposes light from above down to a wafer coated with resist, and that image is captured and transferred, so to speak, onto that wafer surface. This process is referred to as lithography, but you can call it photography if you want. You won't be wrong. Now, let me give an overview of what kinds of processing steps happen before a wafer comes out. So lithography, you already know. It exposes light through a photomask onto a wafer and creates the image of that photomask on the wafer. And then you do various things. You can do etching, which etches away material to complete the design pattern on the wafer. You can do cleaning, because every construction job, especially a high-rise construction job, after every so often you need to clean it so you can proceed. So you remove material that cause defects, you remove material that is no longer needed because it served, say, for example, resist, because it served its purpose by capturing the image, and now it's been captured and etched, and you can remove the resist. There's also this step called implanting. Implanting is a very specific step which implants impurities into the silicon to change its electrical characteristics. And this is the physics trick that we use to make the transistors behave exactly the way we want them to behave, in terms of speed, in terms of how fast it allows in various regions to let electrons move or not move. Depositing is a step or a tool or a capability that allows you to deposit thin films of material, which like metal. And so all these floors that we are talking about, these are just thin films of metal that define the connections on that floor of metal. And then they connect through the posts to the floor above and the floor below. And then polishing. So polishing was discovered as a very necessary step in the 90s, where the wafer surface, after processing certain steps, would become so rough and uneven that it would interfere with a flat image coming from the next step of lithography. So you actually use chemicals and mechanical scrubbers to scrub that wafer, and it's called chemical mechanical polishing, CMP. And so that's a polisher. And then, of course, there is the metrology. Metrology is tools that measure to help you diagnose what's going on. Now, if you notice, I've marked all of the steps except for metrology as what we call value-added steps. That's because they do something to the wafer. Metrology doesn't do anything to the wafer. And it is the most hated evil. Because you're buying a tool, it occupies space, it does all the headaches of owning a tool and using it, but it hasn't done anything to the wafer. It only gives you confidence that you can keep going, or you have to stop. Excursion has happened, something happens because of that. So diagnosis is very important. It's like going for a chest X-ray. No value added, other than just information. Now, one other thing I want to make sure I emphasize is that not all these steps that I've listed are used on every photomask. So remember, there's 50 of them. Some will need it, some will not need it. Implant, for example, is used on selective layers that are used to construct transistors. And so this is not supposed to say that the processing steps for every photomask is is in that is in is comprehensively listed here. It's yes, lithography is for every photomask. Etching also would be every photomask, but not every photomask uses everything else. So now we move on to the next step. Then the next step is to insert the next photomask, go through the same process again, and go on and on and on until all the photomasks are exhausted. And what you got? You got a processed wafer. Hundreds of thousands of dollars of worth when you started with something like a 6,000 or less, actually a lot less. 6,000 is, but a processed wafer that yields all these die is you've created a huge value by going through this process. By the way, do you know how much time it takes to create this kind of a processed wafer? Going through those 50 masks and all the complexities and stuff, it's measured in months. I mean, depending on the complexity of the technology, it could be 2 months, it could be 6. So what you feed the fab today in terms of blank wafers, those processed wafers will come out not tomorrow, much later. So here's, of all those steps, I just wanted to give you a sense of the tool suppliers. ASML in Netherlands, Nikon and Canon in Japan. I listed these as lithography guys. Post-lithography processing, all those things, step-side cleaners and implanters and depositors, all of them, the main players are Applied, TEL, and Lam Research. And the king of metrology is KLA. It doesn't mean they don't have competitors. They do, but I wanted to simplify this slide. So for those of you who are interested in understanding the equipment landscape, from the last slide, the steps, and from this slide, who is playing in what is the emphasis of this slide. So I went through what the process is in terms of sequence of process steps, the tool capabilities, and what it means to build a structure several stories high to build transistors and connect them. But now I want to talk a little bit about what's in a fab operation. You look at fab and you say, what are the operations like? So let's start with, what are the important indicators of fab operations? So safety is at the very top. And with such a complex beast, the safety systems have to be very sophisticated. So one of the sophistication comes from ergonomics concern. So those 25 wafers plus the weight of the FOUP is not able to be carried by people who used to do that, carrying lots between tools and depositing the lot for the tool to process. Humans can't do it because of ergonomic concerns. So that was introduced in 2001 as automatic material handling system. Then there's chemicals and gases. Each one of them can, seriously harm not just you, but also the fab environment and shut the fab down because of contamination and all that stuff. So all those things require safety systems. Then, of course, quality. It's also referred to as yield. Yield is how much. So line yield says, I put in these many wafers, how many came out? And what happened to the ones that are missing? Well, sometimes they accidentally get dropped, but no more because automation is pretty good. And then, or they can be broken inside the tool. When the tool is processing it, when it gets the FOOP, it has 25. So it goes to the first one, takes it, and starts processing it. When it's processing that, there may be a problem with the tool and it can break that. So those are two examples, but that's a line yield. In today's automated, highly sophisticated fabs, it's in the high 99.xx%. We hate to lose wafers, so we design systems around it, and to protect that. And then, of course, die yield. Die yield is how many working die or chips did you get on the wafer. And there are many, many. It's outside the scope of this talk. There are many, many failure modes. You can have a defect, a particle land somewhere and create a short or an open. You can have processing control issues, a misprocessing. You can have variation. You can have the middle of the wafer has great die, but as you go towards the outside of the wafer, it doesn't, because there is a non-uniformity of processing within the equipment. I'm just giving you those two as examples, but there is a whole science, and talk about it in the next slide. Cycle time. How long does it take for wafer to be processed fully? So that's a cycle time. Throughput. How many of these things can you come, so if the fab is equipped to 50,000 wafers per month, your throughput approaches that as close as you can, but there are all reasons why, operational reasons why you may not, one fab may only reach 40,000 and another fab can reach 48,000, and so it'll make a huge difference in terms of the actual capacity of the fab to throw out those number of wafers. Then, of course, there's utilization, equipment utilization. Equipment is a terrible thing to idle. So every minute that it's in maintenance, every minute that it's down, is very expensive. So utilization is very important. And then cost. How much does a fully processed wafer cost? Now, there's two types of costs. Okay, one is when the technologists design the process, design this sequence of steps, and the recipes used in every step by every equipment. When they do that, they have an inbuilt structural cost defined by the complexity of the process flow, which we call the process technology. The fab, once it's in production, can't really change that, but it can reduce that cost by various means, and let me come to that in the next slide. So, on safety, I already talked about no-touch wafer handling, storage, and transport. Then there is the hazardous material, hazmat safety systems. What I'm talking about here is the increasing role of automation in the fab and how it affects various things. Safety, for example, the no-touch wafer handling takes care of the ergonomic issue. But in addition to that, it takes care of a lot of variation that happens when humans get involved in terms of handling lots. Quality and yield. So one way you achieve quality, yield, die yield, is you control the equipment to the finest level of detail. So when an equipment or the tool, it provides you with an interface that allows you to program every nitty-gritty, how much chemical to use, how long to use, how long to heat something, how long. All that thing is an instruction that was designed by the process technology guy or guys who who leave it as a recipe instruction for the tool. So process control. And then while it is happening, in the last 2 decades, we've got this adaptive or advanced process control, where depending on where the tool is going, operating within its area of tolerance, and depending on what its neighbors are doing, you can actually instruct through the automation system how to have the recipe be dynamic. So you can change the amount of time a tool is processing, because you know that this tool, since the last maintenance, has been operating at a certain point within the tolerance range, and so you optimize that. It's an amazing area. Then, of course, detecting defects. Defects are so small, wafers are big, they are all over the place. Some of them matter, some of them don't matter. So you have to detect them, classify them, and do root cause analysis on them. Now, I bunched up cycle time, throughput, utilization, and cost because these play with each other. For example, I can take equipment, redundant equipment, and put it in the fab. That costs money. Utilization will go down, except when you need that equipment to support another equipment or main equipment going out of commission for preventive maintenance. So when that happens, you are saying that my cycle time is important enough that I will sacrifice redundancy, through redundancy, sacrifice utilization. You can increase your throughput like crazy, but for that you need space and you need a lot of equipment. And that has because of bottleneck effect, that has a tendency to generally bring down your utilization and make the cost go up. Now, one interesting thing that the fab can do after it's gone into production is it can consistently decrease the number of metrology steps, because remember, they were not value added. Why? Because you've gained confidence. You're pumping out wafers, the technology is becoming mature. You remove all these steps where you were actually doing metrology and say, it's not needed. We will figure out another way to capture an excursion if it happens, but it's worth it to not have x-rays be taken of your chest every flu season. There's a lot of optimization, there's a lot of intelligence, and in the last 20 years, I've seen I must say, artificial intelligence is playing a big role. Just take a look at defect detection. You can have a wafer map, you can have an image, very, very uh, enlarged image, and you can tell software to say, detect the defects for me or issues for me, and it can do that by self-learning of an increasing number of patterns where it just goes on and on and on and becomes intelligent enough, and so engineers are left to do more of a root cause analysis or action planning beyond that, and not necessarily in detail looking under microscopes. Nowadays we can't even look. It's so tiny you can't even look. So it is that's just one example where AI is used, but AI is used in overall fab scheduling, planning, to optimize the utilization. No tool is idle. Everything is connected to everything. Your tool transport, your wafer transport, and the tool utilization, everything is connected, and you learn, and you have systems that learn and optimize and squeeze the last bit of optimization out of it. So before I go forward, I said my focus in this talk will be wafer manufacturing, but for a moment I brought everything together, the chip design, the wafer and assembly test. And I just wanted to give you a sense of what the ecosystem looks like. So there are lot of people who provide design services or foundry services for wafer manufacturing or PAT services, packaging assembly tests, we call it PAT services. So all of these are service levels. So you can be a designer and not make your wafers, or you can be a designer and wafer maker but outsource your assembly and test. So those are done through services. Then in the design, there's design IP blocks, which is pieces of the design that are most often used and are worth a lot to multiple people. So you basically say, hey, take this, it's ready. You plunk it into your design so you don't have to work on recreating this. So those are the IP blocks. Then, of course, design tools. Synopsys, for example, is known around here because of their generosity to us, but that it's a leading company that provides design tools. And you should never forget talent. Talent is where institutions come also. They are the supplier of talent, and they are part of the ecosystem. So SemiX is a part of the Indian semiconductor ecosystem, if for nothing else but that. Wafer manufacturing and assembly tests, equipment, software, materials, chemicals, gases, water, facilities, power, waste systems, all of them are companies and other people who are part of the ecosystem who are doing that, and of course talent. So that's just one way to simplify the ecosystem and say, categorize and say, if you run into somebody who says I'm an ecosystem participant, identify where they belong in this chart. So far I've never talked about wafer size, nor have I talked about feature size. So let me just say that I got away with that because everything I said so far was common. Okay, well, common in the sense that even though some of those things like automation came in the largest wafer size, the automation applies if you go backwards. But since 1976, and including 1976, there have been 4 wafer size transitions. 100 millimeter diameter wafer, 150, a 200, and then 300. In my part of the world where I come from, it's called 4-inch, 6-inch, 8-inch, and 12-inch. But I have been trained to use millimeters over time. When you increase the size of the wafer, it's an economic boon because the area of the wafer increases by this is proportional to the square of the diameter. So because of that, you're getting roughly 2.25 times more chips per wafer. So even though the larger wafer is more expensive, it's the equipment and the complex, it doesn't matter. When you get 2.25 more harvest, then it's worth it. So why is it? So first of all, Tata in Dholera there's enough evidence through people talking in the press that it's a 300 millimeter fab. So it'll be the largest wafer size, which means all the photos I showed you of automation and everything applies. They will have to get that. As far as Tower Semiconductor is concerned, we don't know. My guess is it's either 300 or 200, but not prior to that. And one interesting thing is that if you notice, the time between wafer size changes suddenly increased to infinity from 2001. Used to be a few years. Now, after 2001, we have never seen a wafer size increase. And that's another story I lived through and I can talk, but it's outside the scope of this. But point is that in spite of industry trying to go, they all settled on this, that it's going to be 450 millimeter. But that's about it. And there's actually wafers existing, 450 wafers existing that are trial, test wafers and all. But the industry is not moving. So that's the wafer size. This is feature size. Feature size can also be looked at as Moore's law nodes. And what are feature sizes? Well, they are roughly a measure of the fineness with which the fab can print, or this technology can print. A fab doesn't necessarily have to be wedded to one technology. It can upgrade its technology to the next level. However, this wafer size is important. Once you are a 300 millimeter wafer size, there is no reason to go back and say, oh, I want to use this fab to do 200 millimeter wafer size. That, right at its birth, you establish the wafer size of the fab. But right at its birth, you don't establish the feature size, but you pick one and then you keep moving forward. So in the case of Tata, the finest feature size that they say they will be able to print using the technology that's coming from their partner PSMC, Power SMC, not TSMC, is 28 nanometer. 28 nanometer was introduced in production in 2010. So it's about a 14-year-old technology, quite popular, quite used, quite popular for the kinds of applications that both Tower and Tata are bringing. And it's a measure of fineness. And when I said it's about 48 to 50 mask plates in the set, I had 28 nanometer in mind. And as I said, if you go much more advanced and pick something from 2022, you're talking about almost double the size of that photo mask set. So with that, I come to what must our response be? And I am glad I've come here and in sufficient time that after this we can have an interactive Q&A or something like that. So first, let's see where we are and then we'll say, what must our response be? So government initiatives are already bearing fruit with fab and assembly test facilities announcements. We talked about that. And with its long history of cutting edge research, talent development, and nanotechnology infrastructure, IIT Bombay has established the Center of Semiconductor Technologies to give focus to the challenge of semiconductor technologies. And SemiX is really thankful to IIT Bombay leadership for this visionary initiative. As it is, we are already 1 year old and alive and kicking and working hard to meet our challenges. And a growing list of industry affiliates, world-class faculty, they allow SemiX to offer industry-relevant training, research, and entrepreneurship programs. Many industry experts, such as me, but I have 7, 8 more people who are executives, advisors, and professors of practice. And beyond them, there is a long list of people who are advisors to us, all industry, many alum of IIT Bombay, and SemiX fellows. So all of that has been achieved in this 1 year. So we have momentum. Now, again, before I go and say what must we do, I want to make an observation on the treadmill challenge. So 60 years of the semiconductor industry has taught us that it is critical to have sustained investments over time. What you see as TSMC today is a sustained investment and government partnership, and of course, success that goes from 1984 or 1986 all the way up to now. There are many such examples. Even Intel, where I spent a lot of time, has had very, very difficult moments where the size of the investment and as a result the percentage of revenue that you had to take off the table and invest um, in risky long-term new fab build-outs and all that, it's nauseating to some people who are risk averse. So, but yet you have to do it. Process technology needs to keep improving. Equipment, facilities, and workforce. This is not a standstill, it's a treadmill. So, although India fabs will initially import existing process technology, in the case of Tata from um, Power Semiconductor Manufacturing Corp, uh, it's in the long run, sustained indigenous R&D will be critical for mission success. So those of us in IIT Bombay who are thinking about what our role is moving forward, part of the role is not to help the fab operate alone. That is true. But also how to get the fab to the point where it's easier for them to ride the treadmill with cutting edge research, relevant research that they have indigenously available to them. Now, once you get on the semiconductor manufacturing treadmill, there is no getting off. Now, that doesn't mean people haven't gotten off. There were 28 companies that I think go back to the 1980s, 28 companies that were manufacturing at the leading edge. I'm not talking about at the leading edge, the fine print, the finer the print, the finer the feature size or the Moore's Law node. So there were 28 people actually chasing that Moore's Law node in the 1980s. Today there's how many? 3. So there people have gotten off and went on to different business models, and that is fine. But if you're in the game, you have to keep riding and investing. So now what must SemiX faculty, students, and industry execs do? Well, we need to gain further momentum in research to enable indigenous development, as I talked about earlier, of technologies from design to manufacturing, not just for manufacturing, design to manufacturing everywhere. We need to lead in the development of India's workforce, not just in terms of capability, but also the scale. Okay? If these fabs come, they're going to be looking at scale. And in order to get all the people that they need to feed these beasts of fabs and assembly tests, well, those people will, innovative ways will have to be found to train those masses of people in what they need to be trained in. And also to help entrepreneurs in hard science startups to broaden India's ecosystem. And collaboration and integration are a must because these challenges that the India Semiconductor Mission faces are big, and they are required to therefore be responded with big goals, and big goals usually require collaboration and integration of effort. So there is a place where the institute can help us also. So SemiX has a request for the leadership of the institute itself, which is to actively engage and encourage and support SemiX proposals to the government and the industry. Come with a conviction to support and back SemiX. Upgrade equipment and facilities infrastructure significantly. We can't say we want to play in this game, but not change the bat and the ball and the wickets that are required to play in this game. Staff, faculty, in critical areas related to semiconductors needs to be there. If there is any area that's missing, we need to make sure that we have faculty that's staffed. And with that, the students and all the team of the faculty that helps to make that area shine. And then, of course, there are some administrative processes that SemiX can identify, which institute leadership can very efficiently and quickly put processes in place that ease the way and improve the speed with which we go through those procedures. And they're all necessary because to achieve SemiX's full potential and to benefit not only the institute but also the country, we need all of the above. So, with that, I've reached closing thoughts, which is just one. And that is, for those of you who are freshly interested in semiconductors, there is a book called Chip War, which is a very interesting story about how the industry and the governments dance together, sometimes against each other, and having technology leaders and business leaders, nations, how that dance brought us here. And the way the story is told is great because Chris Miller is a great storyteller, and he didn't pay me to say that. But it's a good one. If you haven't read it, it's a good one to read because it'll broaden your picture. It's like watching a movie about what happened in history and getting so much that you are now ready to run with what you want to do now. So with that, I say thank you, and I'm open for Q&A, and there is about 20 minutes or so. Any thoughts, questions?
Wonderful talk. As an outsider I don't work in semiconductors, but just curious, among the 50 pre-processing steps that you showed, are there bottlenecks, particular bottlenecks which still remain, or is it sort of a standard procedure which everybody sort of follows? Just like you pointed out, there are cycle time or throughput areas where AI can actually play a role. But in the pre-processing, are there still gaps remaining, or is that sort of solved?
By the way, Sunil, can the persons asking question introduce themselves as well?
Oh, sure. I should introduce myself. So I'm Sakit. I recently joined Whitehouse Informatical Health as an assistant professor. I was a student here actually in chemical engineering in 2014. So I attend talks just because of habit that I had formed in those days.
Great habit. First of all, to clarify, there are not 50 processing steps. The steps are what I listed that are applied from which steps are applied for the processing of one of any 50 masks, right? So the 50 masks have to go through this set of steps, and the overall steps take months to process because each tool takes time to do what it needs to be done, and so on. But there's a set of process steps that are talked about, and then there is a set of mask plates that represent the design pattern on which the steps have to be performed. Now, to the spirit of your question, though, as long as there are things like this, giants like semiconductor fabs and or even space shuttles and all that, as long as we have those kinds of complex things, there is always room for optimization. But I think over time, one of the things about this is When I started in '84 and worked my way through, there was a lot more differentiation about capabilities and how we were proud of stuff that we are no longer proud of because this has reached enough of an understanding of the industry. So the 60 years of history has kind of leveled the playing field, and now it's like squeezing for your own benefit, right? So in some cases, uh, for example, when you have a new design coming in, let's say it's a microprocessor, and you have a new process technology, they meet, and there is a ramp up time which it takes to get to a mature technology, and then we call it um, high volume manufacturing. Now, because of Intel, the way it was, its optimization was to how to shrink that ramp. And we did that because time was money, and we knew that the next processor, people will come eat it out of our hands. So it's best to actually shrink that. So the way we shrunk that was throwing equipment at that, some more discipline in terms of making sure that the technology and the product are rampable, which required a lot of time to be spent in making sure that we had reached a. I think in there, the bottleneck, if you had asked me at that time, I would have said the bottleneck is that period. And you say, how do I solve your problem? Well, give me more equipment, or all of that stuff. So different fabs have different uh, emphasis, and based on that, they will all solve their own bottlenecks, and those bottlenecks shift based on how you solved it, or small variables like a customer suddenly says, this is not that important to me, and then suddenly it percolates through. But the running fab operations, highly automated fab operations, is now quite a level playing field.
Hello. Hi, sir. My name is Mayank. I was also an ex-student here in 2011. So I wanted to know what are the future materials, for the semiconductor industry? Like, is it going to be silicon itself for the next decade, or
Mm.
do you think some new materials are going to come up? And how about OpenAI? This artificial intelligence, new requirements, even in your processing facilities and speeds. So, like, what do you foresee?
Okay, so see, this is the problem with two questions is that as I'm aging, I forget the first. Uh, what the first one was
So, was materials.
materials. Yeah, so there have been forever all kinds of materials, right? The thing is, the biggie is silicon, right? But there is that's because of the volume. It's all it's all volume, right? It's only after I retired from Intel that I came. I realized how much other types of wafers exist and are actually being used. I mean, there was this 2-inch wafer of indium phosphide used for lacing for photonics. So that's a material. Um, Gallium nitride, silicon carbide, these materials for higher power applications, which I'm a digital guy, okay? I know how to make digital, actually, I don't even know how to make it, but I know how to talk about digital transistors as opposed to specialized transistors. So all the cars and automobiles, it is my understanding that the increase in that demand will increase the kinds of wafers like gallium nitride and silicon carbide. And so there are silicon is not the only thing, but the silicon is the big guy. As far as AI, see, at some level, since AI is really a it dines on digital transistors, right? You give more of them, you can change the architecture of the design to make it better for AI workloads and stuff. But from a fab's viewpoint, when the fab looks at that, it's just a digital need. So AI to the fab says it represents demand, not necessarily a major different reaction. It does represent a major different reaction to companies like NVIDIA and people who are trying to displace NVIDIA or come up with other design architectures that will do AI better. That they have to react to it, but the fab reacts to it as a demand. It just comes as simple as that. Now, of course, when you have cars like Tata, for example, or Tower, both of them are saying their fabs will be targeted towards certain applications, which include, automobile market. Well, then you have to come back to part A of your question and say, should there be a gallium nitride line in their facility and so on? That comes from a business decision.
Sunil, thanks for the wonderful talk. Um, sort of, as you said, we should not ask two questions in a row. So my first question, you can take your time to answer it, is that you were at Intel, and I think you haven't talked about the innovation from the universities or the contribution of universities.
Yeah.
And I really
Yeah.
thought that for this audience and for the people out there, I want to know, were universities important to Intel?
Yeah.
In what way? And therefore, what would it mean for the Indian ecosystem? So that would be my first question.
And I'll remember you have a second question. So you are right. I should have actually talked about that. But in Intel, we used to have this concept of the big R and the small R and the big D. R was small within Intel, but the development, which is D, was big in Intel. So how did we afford to keep the R small? The way we did that was we had I'm going to say 15 places of recognized research work going on, where we would identify special senior people within Intel who would take care of the relationship with these institutions and work for 10, 15 years with them before something comes out of it, which we suck into our small r. Because at that point we say, now we are getting into, secret stuff that, what we want to do with it now will be secret to us because now we want to get advantage. But the small r strategy resulted, for as long as I've been in Intel, in fantastic harvesting. Okay, all the transistor innovations that we did, all whether it's FinFETs and before that high-K metal gate, and they came out of universities with our participation, but not our sole participation. There were other people who were also participating. So those two examples. Now EUV, which is have you heard of EUV? It's like a big bus of equipment, the most expensive equipment in the fab. It's if you don't mind, let me just, there's some, this is EUV. Remember ASML? I'd showed ASML as a lithography equipment. This is why ASML is being talked about everywhere, because they are the ones who make extreme ultraviolet light at 13.5 nanometer. It's a big bus. It takes 40 containers, 3 cargo planes, and 20 trucks to move it, to transport it to the customer. Okay? And then when it comes to the customer site, it takes a lot of time, I can't say how much, but a lot of time to actually put it all together. And it costs over 100 million and is considered the most expensive tool. 25 years of research. 25. Now, that was interesting. It included institutions, research institutions, but also this very company, ASML. So, people have retired long before this thing came to fruition, and there are stories. If you look at Chip Wars, the book that I said, it'll talk about John Carruthers asking for $500,000 or something like that to give to these guys so that they can keep going. 25 years. So some part of it is patience, part of it is it takes a community. No company on earth in semiconductors can afford to have their own big research. Therefore, it is extremely important for people like IIT Bombay and other premium research institutions in India to support where the industry. Right now, we are euphoric. There's a fab announcement. It'll be constructed. Construction is awesome. The technology will come from Taiwan. Uh, we need people to run it and all. But think longer. Think longer term. I mean, you think about based on the which way these companies are going, you could be doing some serious research that they can harvest when for their future. Second question.
Thank you, Sunil. So this is an important piece. So universities typically provide research, but also I think there's this whole need for extremely trained students, and they could be from different disciplines.
Right.
So is there a comment on that? That should it be e-specific? Should it be broader? And what is the largest value from any of these research? I mean, I'm assuming most of the research projects never had fruition. I mean, they didn't go into production, right? You didn't make money of them, right?
From
For Intel, right? I mean, you would pay a university money, bunch of papers would be written, good questions would be answered, but
no, there were technology transfers.
right, right.
Right.
But if that didn't happen, would is talent a big piece?
Yes, but it's not because it happens or not doesn't happen. If it didn't happen, so it's fail fast, right? Even in our small R, we had stuff that we rejoiced because it failed. In high K metal gate, there was this approach of gate first versus gate last. Everybody went gate first. We failed on gate first far before anybody realized. We kept our mouth sealed. We were working happily on gate last. Then we watched TSMC come back and say, we are abandoning gate first and we are doing gate last, right? So failing fast or not producing something that I can take and say, oh, see, University of Michigan supply me with this and I put it here and I put this particular capability in this process technology. That's not necessary as long as you have, there is an expected rate of return and it was always considered, that's another one. You can't apply this kind of a thing that says, show me what you have produced. Let it fail. But talent, absolutely. If they are working in that area, they are a source of high caliber talent as well as, relatively lower down the chain fab technicians and so on. So all of that is an institution plays a very significant role. In fact, I was very attracted in last year when we were talking about me joining SemiX that there were three prongs that were given to you. One was industry relevant research, and the other one was workforce development and entrepreneurship. I mean, they are kind of related, and the university is an incubation point for all of that. And in fact, if we reach a point where the university itself can take major breakthroughs and turn that into the finishing, do the big D to take semiconductor technology into market, I think the university is not going way beyond the scope. Having some startups, small hard science startups, take some ideas and go into the market and all that stuff, yeah, that's good. But you can't play the role of Tata. Tata has to do some development. But what you can do as a university is to be that reliable source of, you're right, of research and talent combined. It's not one or the other. That's it. We are done. We have been exhausted out of our questions. I'm fine. Actually, it's 7 minutes before 3:30.
Time for one last question.
One question, yeah. One question.
Okay.
Yeah.
So if you have recommendations for younger generation in terms of
Just hang on for one second.
yeah.
Yeah, so two questions, but related, so you can remember it. So if you had sort of any suggestions, what India should be doing? I understand it's a capital-intensive process, but are there other bottlenecks that we have to take care of, or if the government should be doing something to sort of speed up the process of setting up fabs in India, what would that be? And are there specific areas where there is scope for the younger generation, particularly startups, that could contribute?
Yeah, you should be happy to know that there are so many brilliant people involved in the first question. And, it's like an elephant, and we all see different sides of it, and we describe the elephant from where we are. If you ask me, you know, I have not been driven by this vision of straight high volume manufacturing. It's just, that's not to say that I believe that is a wrong strategy, but that's not what comes to my mind as in my mind, the thing that I don't hear enough of is the collaboration between centers of excellence in semiconductor research, such as IIT Bombay, and a and a indigenous fab that is already in India, that already supplies stuff to the Department of Defense, to the space program, and so on. Lift them up, lift that indigenous fab up and make a tie-in between the research in various institutions and have a grounds up development of technology that feeds the Indian market. And, that fab was started in 1983 and it has survived so far. But that's about it. It only has survived. But I keep going back to this thing where that indigenous research that goes in, has a fab available that does full loops, tape out happens to that fab, and supports all kinds of startups and yeah, identified by the Department of Defense and identified by space applications and so many others. That I would put much more emphasis on. because that part, and maybe this, a Tata Dholera fab and that what I described, which is grounds up indigenous technology development, maybe they can both come together somewhere. But this piece, the piece I talked about, is kind of missing. On the issue of entrepreneurship, I think not everyone. One should understand that not everyone is born to be an entrepreneur, except that now, if you cross that hurdle and you say, no, I am, then you have to say, do I have the patience and the wherewithal to ride this longer term, more intense time, and which may come in the form of a partnership somewhere. So, SemiX is just beginning to define its entrepreneurship program in hard science. And I think we'll learn a lot as we go. But I think my gut says that the support will come in the form of a partnership, the big little partnership, the little partnership, and or those kinds of things. But that's the part of the movie I haven't seen. That's what keeps bringing me back to say, okay, I'm learning with so many other people about how to enhance the Indian ecosystem. But a couple of people have come talk to me about, so what is SemiX, and they've also talked to me about their idea. And 15 minutes into that discussion, I realized the idea is stupid, and the person is not meant to be a hard science innovator because that expertise is in a different area. So just because semiconductors is a happening hot topic doesn't mean everybody needs to descend on it. People need to develop a passion and the staying power to fundamentally understand semiconductors, then become entrepreneurs. All right. So
So let's
we declare the meeting over.
so I just
Okay.
Simon, I think it's a wonderful talk by somebody who has been in the semiconductor industry for many years, and he's here to share his experience with us. He's on site, which means that you can come and pick his brains whenever you want, whenever you like. But this was just one of the first invitations to the community to have a chat with him. So with that, Sunil, thanks a lot. Thanks a lot for doing this. There's a very small token of gratitude, which is the SemiX thing.
I gave the talk for this.
Yeah.
Thank you.
So with that, we call this event to a closure, and thanks for coming.